recording. Thank you very much. ECGR 4101, 5101, lecture number 2. Welcome. Today I'm going to go over a little bit of the remaining of chapter 1 and do some descriptions of some aspects of an embedded system, maybe in a little bit more detail. And then I'm going to start on chapter 2. Chapter 2 I'm actually going to post. I was going to photocopy it, and then it was like 22 pages times 30 people. It's like a ream and a half of paper, and we're trying to cut costs, so I'm going to let you spend money on that. I would recommend you print it out. It's a good chapter, actually. It's a good overview chapter. Some of them a little bit later are going to be a lot longer. So when it comes out, it's a lot longer. Like one of them coming up is going to be somewhere around 80 pages. And that's the chapter on serial communications. But I want to cover a little bit of the background, and I think you saw this picture, and I don't have the actual board with me, although I should have. And there are some aspects of this that I want you to understand, and I actually am going to talk a little bit about microprocessor or microcontroller board manufacturer as well. So if you take a look at what you have right here, it is a... Oh, by the way, did anybody not get the syllabus or a copy of chapter 1? Somebody show up late? All right. Being none, I'll just go on. And that is, when you look at any embedded system, there's one aspect of all of it that is important, and that is the manufacturer. Because remember, what's the main goal of a company that you work for? To make money. All right? Some companies make a lot of money. Some make enough just to get by. Some bleed money, and usually those companies are ones that are closed, or at least they close various assorted parts of it. So I worked for one company called Sony Ericsson that was bleeding money from one side of the manufacturing or one side of the design and manufacturing business, that being CDMA phones. So in one fell swoop, they just said, let's cut all 450 people who are working on CDMA phones, and we're going to concentrate over here on GSM phones. So in one fell swoop, suddenly 450 people working in Research Triangle Park were out on the streets looking for a new job. Some people knew it was coming. I suspected it. I suspected it was coming, and so I was already looking. Other people were absolutely blindsided and had no clue it was happening. So when worst comes to worst, understanding the business as well as the technical side is really helpful in staying alive in your job. So let's take a look at this. Here we have an example of a printed circuit board. I'm trying to get a good, at least image or picture, or being able to have a good, let's see if we do this. It doesn't look any much better. That looked better until they did this. All right, so let me just go over this really quickly. One thing you notice here is it's green. You notice that most circuit boards are green?
Yes.
Why is that? To be environmentally sound. Oh, you get... Who said that? Okay, who wants to admit to saying that? I can take only one. Who's it going to be? You got, all right. You get a free trip to the prize closet. Oh, yeah. So that's for those of you who are watching this on tape. Sorry, I can't shove a prize to you through the internet. You can come visit. I've got squishy ball thingies. You know, let me rephrase this again. I've got stress balls. And I've got, I don't know, pens and paper. Oh, stop it. All right, going back onto this. The one thing you'll notice about this is it's green, which is a fiberglass epoxy-based medium in which they use, and it's primarily useful because it does not conduct electricity. And as you can imagine, you want to have parts of your circuit that do and don't conduct electricity. What do you think conducts electricity? The metal. So oh man, this looks horrible. Let's see if I can get this looking better. All right, does that look better up there? There's got to be a way to fix this.
There you go.
Well, I'll work with this one. It's a picture and it's kind of pixelated, and I should have made a better photocopy of this before I started. So let's see if this actually turns out better. Now the one I have in the book is not as good. So if you look at this very carefully, this is an example of the main processor associated with your circuit, and you have certain things that are going to be inputs and outputs. So for example, if we look at this carefully, right here, I notice something that is actually a connection for an antenna. And so it will use, this is a wireless module that will be able to be communicated, or you can communicate with. This part up here is a serial flash chip. Oops. Is a serial flash chip, meaning that we have this microcontroller and this device up here, which is a, oh, by the way, this is a green eval Zigbee module. Maybe that's why it's green, right? Because they said it was. And we actually took off, you know, this doesn't look good when I look at all this. So we actually took off a big giant metal can that sat over it. And the thing you'll often find is in devices that are RF based, cell phones, things like that, you'll often put your radio frequency parts underneath a metal can because, let's see, most of you haven't been in EE, so maybe this will be obvious to you or not. Have you ever been in our Faraday cage? In our environment? If you surround something totally by metal, what does that metal typically do? It absorbs radio frequency, it absorbs heat. So anything inside of that is immune to outside RF radiation. Well, think, why would you want that? If you have a very sensitive part and you want to actually control what RF gets into that part, you put a giant can, metal can around it, and you give it one little signal going in, usually from an antenna. In the same way, sometimes these parts just radiate lots of stuff, and you don't want all this radiation to get out, so you also put a can around it to keep all this nasty radiation from getting out. For example, in the cell phone, do you want lots and lots of radiation to be transmitting stuff into your head? Usually not. So that's why you direct it to an antenna that's pointing to the outside, and you put a can around the RF parts to keep it from radiating. So that's an example. We have a microcontroller that has lots and lots and lots and lots of pins. These are surface mount pins. The one thing about a typical manufacturing device nowadays is very little is through hole. In other words, see that green epoxy nylon type of device. There's very few things that actually go through. In this case, there are up and down here. It's through hole parts because it actually plugs into another module. But usually, if you get anything and you, let's say from your old cell phones and you open it up, hardly anything goes through the board. And that's the old DIP parts, meaning dual inline package, or any other larger parts like capacitors that you don't want it to go through the part itself because it's harder to manufacture. Something surface mount like this, really easy to manufacture via online or via automated machinery. Have I shown any pictures of that yet? I can't remember what. Oh, I did that in robotics. That's what I did. So let's open up one really quick and show you an example of that. Estimator. So if we look on control, oh, this is this thing again. Something about this screen is not right. I'm going to have to call that in too. I'll see if I can point to this. Here is a movie that I'm going to show. Oops. I picked the wrong one. Never mind. Where'd it go? Oh, here it is. There's a picture of the manufacturing of this movie, and to give you an idea, here is a printed circuit board. It's in a robotic pick and place machine. So you feed it with instructions. This is a camera right here. It has LEDs which will shine up, and then these devices right here are actually air grabbers. And using suction air, it'll pick up parts from reels right here, and it'll place it on this board. And it stays on the board because this board is covered with a sticky solder paste. You've probably seen solder in the little strings, right? You have to melt it. Well, you could have paste that has the same composition as the hard solder that you use with soldering irons. And then you run the paste through an oven, and it will bake the parts on that you place. So if we look really carefully at how it's going to be manufactured, here it is, picking and placing on this unit here. The camera actually looks at the part that was picked up. And if you can imagine, if you're trying to pick something up from a surface, you don't know if it's going to be oriented like this, oriented like this. So the only way to know exactly how it's oriented is to take a picture of it as it's being lifted up. And that's what that did at the end with the camera. Because you have to place it exactly where it needs to be on the board. As another example, here's another movie of it. And here's it's showing an example of placing again on the board. And notice there's one of these on each side. So there's one of these pick and place arms on both sides that is filling the single board. That way, while one is picking up and checking the orientation, the other is actually putting it down on the board. And that's why it's so much easier to do manufacturing with surface mount parts, because if you do it with human placing and human soldering, it takes so much longer, a lot more expensive. So almost everything nowadays is done with surface mount devices and surface mount parts. All right, that is about all I wanted to cover in chapter number 1. So now let's start up with chapter number 2. Chapter number 2 is going to be posted on Moodle. I decided to put it behind the Moodle firewall, and I would really appreciate it if you guys didn't share it with anybody else yet, because it's page proofs, exactly what it sounds like. It is proofing and saying, is this right? So as an example, in my page proof for this, the note for the author says, hey author, is this alignment okay per the email of 8/18/11? That means that the person who is working on this book and typesetting it and making it all ready to be printed is asking me a question of which I'll have to answer. And obviously it's not going to be in the final book, so I don't really want that hanging around too many places. But it's we're giving you the opportunity to get a look at this book early. So again, for lecture 2, we talked about in chapter 1, manufacturing. Example of a printed circuit board. And you already saw some of that last week. So today we're going to talk about the basics of embedded systems, specifically the whole idea of how you design an embedded system using microcontrollers. So as you can imagine, there are two concepts that you have associated with the world today. And they are just really, really, really high level. What are two major divisions of electrical and computer engineering? Working with signals, working with data, working with anything. If I say one is analog, what's the second one? Digital, all right? Yeah, that's kind of easier than you thought it would be, right? All right? If you think about everything in electrical and computer engineering, what are you doing? Well, you're looking at the world either analog or digital. So what's some examples of analog that you know of? Anything in the world. Radio. What about the data in the radio waves? You might represent data in digital format in those radio waves, right? That's interesting. Well, let's look at something a little bit more meaningful. Well, what else?
Amplifiers.
Say it again?
Amplifiers.
Amplifiers, or you're thinking of power, or for that matter, voltage?
Oscillators.
Let's think of digital. What do you think of? Representation of pictures. 0, 1. Microprocessors. So simply think about this. This comes all to the root of electrical and computer engineering. Analog means continuous voltage. Continuous voltage. And digital means discrete. 0, 1, 0 volts, and VCC. So think of the entire world now. What do you measure in the world that is analog? Phenomenon.
Power.
Is it power or voltage? Light. Sound.
Light speed.
How about digital?
Bits.
Isn't that kind of controversial, the light?
What?
I thought that light was like those, they call it like packets. Like,
Oh, light packets. Why are you getting too much into this? All right. So, is light continuous? Well, let's see. It's not completely 0, right? It's somewhere between 0 and 1. And this isn't truly 1. I bet you I can make it even brighter. So, again, when we're looking at measuring light, we're going to have to say, what's a reference for the maximum? What's a reference for the minimum? And where does this fit? Somewhere in between. We're going to look at an example of A to D conversion later. Digital is simply on and off, presence and absence. And also sometimes we're going to have devices which will measure analog and convert it into a digital format that we could use. Because an awful lot of the world is measured in and represented as 0 and 1. So, continuing on. If we are working with our digital system, we're going to have the following happen to us. We will actually say, we will have input come into our microcontroller if we want to grab 1, 2, up to 8 different digital lines, we will have it come in this way, and we will give this 0 volts or VCC, whatever VCC is. 10 years ago, VCC was 5 volts. 4 years ago, VCC was 3.3. More recently, it's down to 1.8. And I've heard of some chips now running at 0.9 volts. That's really low. Why would you want to lower VCC as time goes on? All right, here everybody. Say that again?
Power consumption.
Well, it goes beyond not only power consumption, probably one more important. Heat. Heat is destructive for a microprocessor, and of course, if you generate heat, which is generated from resistance in the chip itself, you have to find some way to get it out. If you're packing more and more transistors in a chip, you have more and more transistors turning on and off, generating heat. So you can keep the same heat in a transistor that's running at 0.9 volts than one that has half as many transistors running at 1.8. Actually, it won't be exactly the same. It'll be something different. But yeah, less voltage, less heat. You can pack more and more stuff on it. And again, the worst thing you want to do with silicon is boil it. And you'll boil it by making it too hot. By the way, I'm sure many of you have done that. You've released the magic smoke from parts, right? Suddenly you're working with something and you see the little puff, and then it doesn't work anymore.
It smells good.
And it smells really good, yes. So when you release the magic smoke, your part no longer works. So make sure you don't do that. All right, so when you're talking about input and digital, this is called a port. So a port will be a device, or it will be a part of your chip that will accept digital input. And in fact, you can create a single port and represent it by a single name or a single letter by calling this something like ST port 4. Which means that it's going to be port number 4, and it's assumed that ports are 8 bits. Not always, but it's just assumed. Now, when you have a port like this, you need to identify, okay, is this really going to be input or output? And the nice thing about microcontrollers is you can make a port input, output, or both. Well, not at the exact same time, but you could change it. And the reason being is that some ports need to be inputs, that you need to gather data from them. Some are going to be outputs. You're going to control lights and motors. Some you might change. They might be a communications port, that sometimes you receive communications, sometimes you send it out on the same exact wire. So you need to do that. So what you're going to see with a port is port direction. So, if you remember from your computer architecture class, that's why you had that class first, you had a concept called registers. The way for you to read what's going on inside of your microcontroller is to use registers. So you'll have data registers, you'll have control registers. The data registers are exactly as you can imagine. If I were to say this is going to be 0101, 0101, and I would say what is on ST port 4, the answer is
55 hex.
all right. I hear 0, I hear 1, I hear 55 hex. There's one other type of answer you can give me. So here's a question. If I declare this as 8 bits, which direction? So what we often have, or where does it start, where does it end? So in our example earlier, I'll say, here is my port number 4. And I'll say that this was port 4, bit 0. Port 4, bit 1. All the way down to port 4, bit 7. And then I might organize it as follows. Oh, this is ST port 4, and I have how many bits? 8. And so this will represent bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. And so what would be the contents of this if that's what I had as my input? 1 0 1 0 1 0 1 0. And this is a data port. And then the neat thing about this would be, let's say I want to read it. Let's say I want to say, what is the contents of that port? And I want to store it as a variable. And let's say earlier I had said, and let's say earlier I identified some C code where I said int my input. Is that correct C code? Yes. I also say somewhere my input is equal to ST port 4. And that would give me, can you see that? Okay. So that would give me the value of my input would be what?
The address of the
Say that again?
The address of the register.
I can't hear you.
The address of the register.
Are you sure?
The port is somebody. The name refers to the address.
The name represents whatever the data is there. And I'm going to talk later about addresses later, but I want to just do the really easy base.
Gives you 170.
So this would be, and by the way, this is why I expect you to know all the values, right? That is 2 plus 8 plus 32 plus 128. All right? So that turns out to be
170.
So, the other aspect of this that you need to understand is that, as I said, each one of these ports, as we discussed earlier, could be input or output. So then we also need to identify what the port direction is. So port direction is controlled with another register, in particular a direction register that's associated very similar to what the data register will look like. So I'm going to actually take an example of this, and I'm going to show you what it looks like in the language that you're going to be using. So actually in our RX62N, we would say something like port D, DDR, byte is equal to 0xFF. I'm sorry, I got it the other way. 0, 0. Ones would say it would be an output. All right, so let's take another example that shows as a input, or as an output. So let's say we had a circuit like this. Wow, I can't even show you this because it doesn't look too good. So I'll just show you a neat little circuit.
Can you go up?
What is this?
LED.
LED. Why is that resistor there? Does anybody know why that resistor? Just raise your hand. Anybody know why you have to put a resistor there? All right. I want to find out how many people know. All right. So obviously I need to cover this, right? Oh, this is sad. You should know this already from your original electronics. What if you didn't have the resistor there? What would happen?
Too much current.
Too much current would flow through the through the diode, and you would most likely burn it out. So that resistor is a current limiting resistor. By the way, should you have the resistor on this side of the diode or on the other side of the diode? I've always asked people that. Does it matter? And technically it doesn't, but it's usually better to have the resistor on the 0 volt side. So this would be your port, and let's say this is in our example here. It's we'll label them. As opposed to a number, we'll label it port D, all right? So this is port D, and this is bit number, I'm going to do this so it matches the book, 0. So it is port D, bit 0. So as a way to put this as an output, I want to make sure I link this up correctly. We first need to identify this as an output. So we will say that this is port D, since it's port D, not port 4. The direction of bit, specifically bit 0, is going to be equal to 1. And this C code will allow you to set that specific bit as an output. Next, to be able to output something to it, oops, forgot to add this, data direction register. So to actually write something out, port D.dr.bit.b0 is equal to 1. Light the LED. So as you can imagine, the whole idea of this is you are wiggling the bits and wiggling the bytes of the inputs and output ports to be able to do the work associated with your microcontroller. The other concepts you need to get out of this, by the way, this says data register. This stands for data direction register. And that's how we will be able to work with all of the ports, directions for regular digital output and digital input. Now notice what you don't have here. You have no idea what the address is, do you? So the actual address of port D.dr and port D.ddr is in an include file. Because imagine this. Let's say I have this wonderful part, and this is the RX62A, and I have this wonderful one here called the RX62N. And I'm actually designing my device that will use either one of those parts. As you're compiling code, you do not want to have to identify which one of these two parts you're going to use because they may be manufactured quite differently. For example, this one might have, and I'm just going to pull a number off because I don't have it really handy what the actual address is. I'm looking to see if I can find it. Nope, I cannot find it, so I'm not going to claim it is. But let me just guess and say that in this case, port D is equal to memory location 000010 00E. I'm just making it up, so don't don't think that that's what it really is. But maybe on this part, port D is actually 0000103E. What I don't want to do is have to put all throughout my code, everywhere, what the address of port E is or D is, because it may change depending on my device. And these are the same family, but maybe the difference between this one is that this has 32K of flash, and this has 1 meg of flash. One is more expensive to the other, so if I make a small device, I'd want to use this one because it's going to be cheaper. A bigger device that needs more code, I'd want to use this one. So we have include files. The include files, and I'm going to cover this in a later chapter, have a mapping from ports which is a data register, to hardware addresses. And hopefully you picked this up from computer organization, right? About what is an address, how you actually access addresses and all. And I'll go into that in more detail in, I believe it is chapter 3, where we're going into a lot more detail about what addresses exist for the data ports and the control ports. But I just want you to keep the concept that there is a concept of, where'd it go? Registers that you work with data, and registers that actually control the data registers. So what did we see for this just simple digital input and output? The data register was known as port D.DR, and that's how you defined it. And then the control register, which identified if it was going to be used for input or output, is port DDR. Direction data register. That is one of the general concepts I want you to get out of today. The remaining talk about today is going to be now how we can use this microcontroller to do other things like analog, taking in analog signals and outputting analog signals, and how you might want to hook up other things. Excuse me. So, let's move a little bit forward. I really wish I had this for you before I started, so I apologize for that. Oh, I'll just use one other concept too. And that is, if you want to use, I showed you how to hook up an LED. What if I wanted to use a port as an input, like a button? So here we have a microcontroller, and we want to put a button here, some sort of switch. What do you think I'm missing right here? So when the button is not pushed, what's the voltage right here? All right, I have VCC and I have 0. How do you know it's VCC? Okay, if it's 0, how do you know it's 0? So if you don't know what the voltage of that is, and you're not tying it to 0 or ground, what is that called? It's called floating, right? So because we have not tied this specific input to 0 or ground, you have no idea what that is. So it's just floating out there. Now when you push the switch, what is the voltage going to be? 0. You know that for a fact because you're suddenly tying it directly to 0. So when you release the switch, you don't know what it's going to be. So what do you think you want to put it at when the switch is not pushed?
VCC.
All right, VCC, or as close as possible. So if we hook this up directly to VCC, what would we have going straight from VCC to this ground? That would be a short, right? You have a direct wire. Is that good? No. Not only as it gets hot, it pretty much makes the battery really hot, and you drain the battery really fast. So what's a good device to put in between? A nice big resistor. And this big resistor will have some sort of value which will ensure that you don't have much current that you're wasting between here and here. But it will be as close to VCC as possible. Because as you can imagine, our microcontroller is going to be looking for 0 volts, and it'll be looking for VCC, and it'll probably expect a little bit above here for logical 0. And right near VCC, it'll probably accept a little range there for 1. And then there's this no man's land in here that you really don't want to reside in. So we usually want to have a value here that would be a very large resistor or a very small resistor.
Small.
Right, a very small resistor meaning something in kiloohms, right? Milliohms, huh? So, what I want you to do is to turn to your neighbor, and assuming that this is port C, I'll just call it that because I think that would be, you know what, I'll give you port D. Assuming that this is port D, we'll call this bit 0. Write the code to set the direction of that bit, and then to read the bit and put into the variable my input. So, spend a couple of minutes to do that. You can turn and talk to your neighbor. I like to have these times where you actually turn, talk to your neighbor, try and figure out what's going on.
This is pretty sweet. This bit 0. So this 1 or 0 determines whether it's a...
Yeah. I'm assuming
So the output, what was it equal to? This is the previous example. The port D.DDR equals dot bit, whatever it equals 1.
And what's the direction?
So if you want to specify that as an input, you can specify that as equal.
Oh, as your variable name?
No, you specify the port DDR.
Yes.
That specifies the direction.
Yes.
How can we, what differentiates the specified output?
Like in serial?
Yeah, we wrote
Well,
this slide code.
okay, right. It's a direction, and you read the bit.
Here, I'm going to change it. So I'm going to call this port 4. So just call it port 4. Just change the D to 4. Come on, you got erasers, right?
She said, she wrote one. Yeah, I guess that's there's no one whether it's yeah, that's the only thing
So far, I don't know what this would be.
All right. Who's not done yet? Who's lost? All right. We got a couple of honest people. So, you want me to just show you the example or have you tell me? Yeah. This is what I have. What do you think? Is that right? Ooh, I got this. It's kind of...
Oh, no.
I did something here that's rather interesting, which I should have done earlier, I believe. I should have done it earlier, too.
Yeah.
So I'm going to change my notes earlier.
Did you say input? You want you want input, right?
Yeah, I mean, you could.
So why did I write this int right here?
Casting the value of the port.
All right, I'm casting the value of the whatever I'm getting, saying now fill an entire integer with this value. So what I'm doing is I'm converting the binary to an integer.
Integer's what, how many bits?
It depends. Integer is how many bits, and the answer is whatever your compiler says it is.
Is there like a minimum or like standard?
It all depends on the architecture of your device and how wide its word is. So, for example, we have a 32-bit machine. So I gotta check to make sure, but I believe for our 32-bit microcontroller, an integer will be 32 bits. In the old Renaissance board, our word was 16 bits, and so an integer was 16 bits. All of this should have been taught to you in computer organization, right? You get that? You remember dusting off the cobwebs since it was a year ago? You kind of, no? Just dust off those cobwebs, all right? So here's the next assignment for you right now. I like to do stuff in class because otherwise, it kind of makes you actually be active and do something. Let's say I have this device right here, and this is port port 4, bit 0. Here's my switch, right? And here is my LED. Oh, I'm getting fancy, yeah. And this is port D, bit 0. So write the code. 2, number 1, set the directions of everything. 2, read the button. And if pressed, light the LED. Do this forever. What is the line of code saying do this forever? While 1. So I'll give you a hint. The answer is going to be while 1, and then there's going to be a lot of stuff inside. Although I could also say the direction of everything, you could put outside the while loop. Yes, sir.
Can you pull it down?
Is it super bad if you put the direction in the while? No. That's not bad.
But unnecessary code will be executed all the time, right?
Well, that'll mean it executes all the time. Is that bad? For our simple machine, no. But when you're doing a real embedded system, yes. So I think I'll have my guy who got the trip to the, what do you call that? The prize closet. I'll take your solution. No pressure. By the way, you guys can feel free to talk to each other. You know, this is when I say go ahead and talk to each other. You know, you do a lot of learning by actually saying, what do you think of this? Oh yeah, what do you think about that? Yeah. So go ahead and talk to each other.
They're both bit 0 because you have 8 bits.
Oh, it's 4, right? There's 4 and then there's this V.
Yeah, this
But it's
is
the
actually
V is going to be,
okay, and this is the output.
okay,
The button is
Which one is
pressed.
writing in the
Because you're
I guess the output would be.
well, but initially whenever I said direction,
For input?
for direction,
It's either one.
then
0.
Yeah,
Output is 1.
I guess it's.
so
This means you
Because we just see that the first time.
take that, because I already have that.
I said you can put the direction one house up. It depends on the scope of the application.
What's going to happen if
Reasonable ground.
We're thinking about rounding to a certain
I guess.
versus like you press a button, that's a 1. Don't press a
I
button.
guess like
Yeah.
yeah, the DR. I guess when that equals
It means it's 0.
the other one would be buttons pressed.
Yeah, the other one would be one.
Well, I could have done it if
Then the LED will be like so it's like that be more.
so then
Like you're comparing, you want to check to see if the LED is one, the button is one.
The button is one, yeah, the LED would be one. Otherwise, zero.
Okay, so there would be a.
Yeah.
Okay, that's what I'm assuming. Yeah.
He's counting the vents already, so while one is bracket.
No, the only reason why is because it's reader button and it.
All right, who's not done yet? Oh man, you better hurry up because I need your solution. You're gonna do it at home, you promise.
No, I said you really don't need my solution.
Oh, I don't need your solution. That makes me so sad. All right, I did mine in 6 lines, including the while and the curly at the end of the while. And I didn't need to define a variable because I didn't ask for one.
Did you do the else statement?
Pardon me?
Did you do the else statement?
Yes. I didn't if else. Anybody want to see my solution?
Yeah.
All right, I bet you it would be on a test or a quiz. You never know. All right, let's see if you like this one. All right.
oh,
Does that look appropriate for the setting the direction?
Yeah.
So port 4 is in.
So one.
well, what?
Yep.
I thought
It just says not, which is making it easier.
Oh.
You could, it's the same exact thing as this.
It's just why did he say port 4?
Waiting for you guys to make an observation.
Versus port 2 being an input.
Yeah, that's wrong.
What did you set that back?
Port 4 is the inversion.
Say that again.
Where's your thing?
I can't. You got to speak up.
Where's your van?
You don't need it. You don't need it.
It's in the bracket.
Port 4 needs to be 0. Port D needs to be 1.
Yeah.
Yeah.
I noticed that as soon as I wrote it and threw it up on the screen. So, hence I'm testing you. Yeah.
Don't you also need a semicolon at the end of the if statement? At the very end of the line?
Nope, because you have an else.
It's actually technically
You
one
still
line.
need a semicolon.
It's still technically one line of code.
Yeah, it's one condition.
No, I'm talking.
No. All right. So you agree that that works,
Oh,
right?
he said if not. Okay.
Yeah.
Push
I
button.
see that explanation.
Input. LED output. So, if not, the data register bit, not meaning 0, 0 meaning you push the button, 0 volts, right? So, if it's not 1, that means you've pushed it. So I've pushed it, which means I light the LED by giving it a 1. Else, that same exact port, I set it to 0. Notice I have to do both. I have to set it to 1 or 0.
If you don't, it'll either turn on or stay on.
Exactly, because if I don't turn it off, it'll just stay on even though I take my finger off the button.
Not NC, right?
So, have we had enough? You bet. Was that exciting and fun?
Absolutely.
All right, here I should make a vote. The guys who didn't turn in their quiz, they were late. Should I accept their quiz? All right, I'll be nice. Bring your quiz up last time. You got to make sure you turn it in when I give the quiz. Thank you very much. You can turn that off.